Good afternoon, all. Okay, now from from last few sessions, we are discussing design of the plastic parts. Now, in this today's session, we are going to discuss the uh, tolerances and allowances in the plastic parts. Okay, what is the meaning of tolerance and what is the meaning of allowance, and which kind of the tolerances you have to provide means tolerances will be there in the plastic parts, and which kind of allowances you have to provide in the while designing the plastic parts that in today's session we are going to discuss in brief. Okay, uh, first I will start with the what is the tolerances, what is the meaning of tolerance. Then we'll go through the factors affecting the tolerance. After that you will see the what are the different types of the tolerances which we are going to provide, means which we have to study for the, and these are related to only plastic parts. And after this, what is the meaning of the allowance, which kind of the allowances we are going to provide here in the while designing the plastic parts, and short description related to that allowances. Okay, this part we will going to cover in this today's session. Okay, we'll start with this tolerances in the plastic parts. Okay, now first of all, you have to understand what is the meaning of tolerance and what is the meaning of allowance, and what is the basic difference between tolerance and allowance. Okay, so basic difference in the tolerance you will able to understand with this. Its concept or definition itself. Tolerances are unintentional variation that occurs during the manufacturing. Okay, so why this means there is a difference in the dimensions of that component during the manufacturing, because dimensions of the product, whichever dimensions are required, it is very difficult to manufacture a component with the exact desired dimensions. Okay, it is very difficult. And why it is difficult? Because of the certain parameters. Generally there are three parameters that will affect, or because of these three parameters it is very difficult to manufacture a component with exact required dimensions. Okay, suppose you want to manufacture a tube having 10 millimeter diameter. Okay, then it is not possible to manufacture the tube with exact 10 millimeter dimensions. You will end up with a tube with 10.01 millimeter, 10.02 millimeter. Okay, so why it is not possible to achieve this? Because of the certain parameters that is affecting the process. And what are that parameters? Okay, generally these three parameters will affect whichever process you are doing, whichever manufacturing process you are using to give the obtain the desired shape and size. It will be affected by with the material shrinkage. Whichever plastic material you are choosing here, then it will be subjected to some shrinkage. There will be some shrinkage, and due to that shrinkage during the processing, some shrinkage will occur. And due to that, what will happen? You will end up with the means you will not get the desired dimensions. Okay, you will end up with some unintentional variation in your final dimension of the final product. Okay, that will be termed as and whichever uh, you are considering the part is acceptable. Suppose you want to manufacture a component having the diameter tube with suppose internal diameter 5 millimeter, then you will provide a value 0.02, means that much variation. If suppose you will get the product having diameter 5.02 millimeter, then it will be accepted. Above that it will be rejected. That will be termed as the, that value will be termed as that 0.02 millimeter. It may be above that value in desired dimension, or it may be below. Okay, it may be 4.98 or it may be 5.02. Within that range, whichever product is manufactured, that will be accepted as a final product. Okay, and that value which you are providing plus minus 0.02 millimeter, that will be termed as the tolerance. Okay, this is the unintentional variation. It is automatically happening during the manufacturing process itself. And why it is happening? Due to the material shrinkage, or due to some change in the process parameter from cycle to cycle. There may be some changes in the process parameters, slight changes in the temperature, or slight change in the pressure, that may change the dimensions of the final product. Okay, and there may be, and the third parameter which will affect the dimensions of the final product will be position of the gating system. Gating system is nothing but the arrangement which consists of gate, runners, and screws. Okay, means through which the molten plastic material will flow into the mold cavity. Okay, that is termed as the gating system. Okay, depending on this gating system and depending on the cooling channels which you are using to cool that molten material, plastic material, after pouring it into the mold cavity, you are cooling it, and whichever cooling channel you are using, depending on that, some changes may occur. Okay, whichever changes are occurring here, these are unintentional changes. Okay, these are, means due to the some changes in that process parameters, or due to different gating systems or cooling channels, or due to the material shrinkage, these are unintentionally occurring. Okay, these are not provided by the manufacturer, they will automatically occur. And you are providing certain value, and that products can be accepted within that range, that will be termed as the tolerance. Okay, in short, you can say that tolerances are unintentional variations that occurs during the manufacturing. And this variation is occurring due to the following parameters. We can say that the material shrinkage, then variation in the process parameter, then position of the gating system, and the cooling channel. Depending on these three parameters, you will end up with the some difference in the final dimensions, that will be termed as unintentional variation, and it is known as a tolerance. Okay, it is known as a tolerance. Now, uh, now this tolerance will be different for different material. Okay, you cannot say that for all products zero point zero 0.02 or zero point 0.1 or 1 millimeter tolerance will be there. Okay, this will change from material to material. It will change from material to material, or from product to product also. Depending on your need, you can change it. Okay, then one more thing here. Okay, this is the you can see the one, two, and third. Please refer this third point. Some you can so that some MCQ, multiple choice questions may be there. Okay, multiple choice questions may be there on this point. Okay, one example, some information is given here. Okay, in case of, suppose you are using a single cavity. Okay, you are using a single cavity mold, and if tolerance provided is x millimeter. Okay, x millimeter, then for every additional cavity, okay, for every additional cavity, tolerance will be increased by 5% of the x. Okay, you have to make some changes here. 5% of x. Okay, if you are using the single cavity, if you are using a single cavity and tolerance provided is, suppose 10 millimeter, tolerance provided is 10 millimeter, and Suppose you have manufactured, suppose one single cavity mold is there, and you have provided X millimeter tolerance. Okay, and when you are going to increase the number of cavities for each additional cavity, you have to increase that tolerance by 5%. Okay, whichever initial value you have used, for that initial value you have to increase for each cavity by 5%. Okay, suppose one practical example I will give you. Suppose for a one product, tolerance you have given is plus minus 1 millimeter. Okay, plus minus 1 millimeter is the tolerance provided, and this is for single cavity. For single cavity, 1 millimeter tolerance you have provided. And now suppose you have gone for 10 cavities. Okay, you have gone for 10 cavities. Then what will be the tolerance? For each cavity you have to add 5% of the initial tolerance. Okay, initial tolerance is 1 millimeter. For one cavity, 1 tolerance you are providing. Then what will be the tolerance for 10 cavities? Okay, these types of numerical questions may be there. Then your answer will be, for each cavity, for each additional cavity, the tolerance will be increased by 5%. Okay, for 10 cavities, tolerance will be increased by 1 is the your initial, and for 10 cavities it is, you can say that 5% for each, and your final tolerance will be 1.5 millimeter. Okay, you can do these calculations with the help of pen and paper, or you can do it on the calculator itself. Okay, just you have to remember here, if suppose for a single cavity tolerance is provided X millimeter, then for each additional cavity you have to increase the tolerance. You have to increase the tolerance by 5% of the initial tolerance value provided. Okay, uh, number of times they have asked this question in the MCQs. This is very important question. And then after this, we will move towards the next point. Okay, while giving the tolerance, okay, while providing the tolerance, some extra factors related to the, you can say that the working conditions, you have to take into consideration here. That extra points or factors we have to take into consideration are shrinkage of the parts. Okay, shrinkage of the parts, then manufacturing tolerance, and abrasion loss. Okay, one by one I will explain here. Now, due to the shrinkage, okay, this is the normal process. Shrinkage will occur here during the solidification. Shrinkage will be there, and for this shrinkage, okay, for this shrinkage also you have some, due to this shrinkage, it will, some value should be there in the tolerance. Okay, to cover the shrinkage. Then for defects, or some process defects, or suppose you can say that the working conditions or manufacturing process defects or variations may be there in the parameters. To cover that, some manufacturing tolerance is provided, and during the production process or manufacturing process, some loss will be there due to the abrasion. Okay, to cover that also you have to, uh, while giving the tolerance values, you have to cover this also. Okay, means these three factors you have to take into consideration. There may be some changes due to the shrinkage of the part, and due to variation in the manufacturing processes, that is manufacturing tolerance, and due to the abrasion process. Okay, you have to consider all these factors here. Then we will move towards the next point. Just a simple case you have to uh, remember in this tolerances. Tolerances are unintentional variation that occurs during the manufacturing. And why these unintentional variation is occurring? Due to these three parameters: material shrinkage, variation in the process parameters from cycle to cycle, and position of the gating system and cooling chain. Okay, then we will move towards the next slide. Now, in this slide, here some parameters influencing. Okay, these parameters will affect the part tolerance. These parameters will affect the whichever part we are manufacturing. These parameters you have to take into consideration. This will change the tolerance values, okay, or some dimensions of the whichever product you are manufacturing. Dimensions will get changed. So first point in that is the part design. Okay, in this part design, whichever shape and size is there, you can say that the part configurations. Okay, depending on the final dimensions required, according to that this tolerance will be given. Okay, tolerance value will be provided. Then in this material selected, whichever material you have selected, you have to take into consideration its chemical composition. Then its whatever amount of the fillers or additives are added in that material, then how that material is going to store. Okay, means in short, properties related to the material going to be used for manufacturing the part. First will be the shape and size of the product, or you can say that the configuration of the product required to be manufactured. Then material which we are going to use, all properties of that material, like its chemical composition. Then any kind of means which kind of fillers or additives are added in that material, that you have to consider here. Then the third part is, or third point in this is the mold design. Okay, in this mold design, how this mold design will affect the tolerance. Now depending, if suppose you have changed the number of cavities, if you have changed the number of cavities, then size of the cavity, then automatically tolerance will be affected. Okay, in this mold design, suppose you have changed the number of cavities or size of the cavities, then suppose if you have changed the arrangement of your gating system, okay, means dimensions of your uh, runner, gate, or screws you have changed, then depending, it will affect the tolerance. And suppose you have changed the cooling channel arrangement, or ejector pins arrangement you have changed. All these will come under this mold design, and any changes in this. Okay, I will repeat it again. In this mold design, uh, suppose you have changed the number of cavities, size of the cavities, then any change in the dimensions of runners, screws, or gates, then any change in the ejector pins, that will affect the tolerance. These factors will affect the tolerance values. The next factor you have to consider, or that will affect the tolerance, is the machine capacity. Okay? Machine capacity. Now, this will this in this point, suppose you are using the same machine, or while manufacturing any component, we are using same machine to manufacture number of components again and again. Now, while operating that machine, while manufacturing any component, we will go through the machine only, and this machine will operate under different parameters like temperature, pressure, time, or velocity. Okay, there may be some variations. Okay, as you are using it again and again, if suppose some variation occur in that parameter, machine's parameter, then it will affect the part tolerance. Okay, you have to take into consideration this machine's capacity. Okay, and that machine's capacity to give the accurately and repeatedly that required temperature or required pressure, and to perform the same operation again and again in the specified time. Okay, how that machine will perform the same action again and again with the accuracy, that parameters you have to take into consideration, and these will affect the value of the tolerance. And the last point in this is the molding cycle. Okay, here to perform the same action again and again, here with the lowest cost, that you have to take into consideration this molding cycle. Okay, you have to repeat the same cycle again and again with the least cost. Please confirm that, sorry, presentation is visible or not. Please confirm it whether presentation is visible on screen. Wait, I will share it again. Okay, I think now it is visible. Okay, so we have discussed this point now, factors affecting the power tolerance. Okay, and in short I will explain it. The power design, whichever shape and size of the product is required, that will affect the value of the tolerance. Then whichever material you are using, the chemical properties of that material, its chemical properties and its composition, that will affect the value of the tolerance. And then the mold design, in this mold design, number of cavities used, the size of the cavity used, then the design of the gating system and design of the cooling channel, all these are the parts of the mold design, and this will affect the power tolerance values. Then the capacity of the machine. Okay, capacity of a particular machine which you are going to use to give the desired parameters like temperature, pressure, and then which required time, all these parameters will depend on the capacity of the machine. And how that machine will give these parameters accurately and again and again, means repeatability should be there in the accuracy. Okay, and that you have to consider, that particular parameters, that you have to consider how that machine will provide you the accuracy again and again, and according to that, it will reflect in the tolerance value. Then last parameter is the molding cycle. Then different variables are there that you have to consider. Different variables while providing the tolerances, you have to consider these variables. It is the mold maker tolerances, and then plastic material shrinkage variance, then molding process techniques. Okay, already I have discussed this here only. Okay, variation in the process, this shrinkage, only extra parameter is mold maker's tolerance. Mold maker is nothing but the manufacturer of the required mold. Okay, some tolerance should be provided for that also, manufacturing of the mold also. Okay, so after this we will move towards the actual tolerances. Which kind of the tolerances are you have to go through for these plastic parts. Okay, mainly two types of the tolerances are there in the plastic parts. You can clearly see here, manufacturing tolerance and operating tolerance. Now in the manufacturing tolerance, in the manufacturing tolerance, means whichever tolerances are related to the manufacturing process of that particular mold and as well as the part that are considered here. Okay, these are the manufacturing tolerances. And operating tolerances, these will consider the operating environment. Okay, with the tolerances are required to provide to cover the environmental factors or some environmental parameters that will affect the dimensions of the part. Now, in this operating tolerances, four parameters you have to consider. That is the change in the moisture you have to consider, then change in the temperature, then swelling due to the conditioning. Conditioning is nothing but here we are providing the heat to the plastic material and we are doing the cooling. Due to this, some conditioning of that raw material will occur. For that you have to provide some tolerance. That is the tolerance provided to, for the swelling due to the conditioning. And then post shrinkage tolerance. All these four tolerances you have to provide, or you have to provide this value in the operating tolerance itself. These four factors you have to consider, and for these four factors you have to provide the operating tolerance value. Okay, and this operating tolerance value will be added in the manufacturing tolerance, and total tolerance is provided for manufacturing of the particular plastic part. Okay, I will repeat it again. Total tolerance, while giving the total tolerance, in this you have to consider two types of the tolerances: operating tolerance and manufacturing tolerance. In the operating tolerance, four factors you have to consider. That is the post shrinkage tolerance, then swelling due to the conditioning, change in the temperature, and change in the moisture. By studying these four factors, operating tolerance is provided for that particular material and for manufacturing that particular component. Then the manufacturing tolerance. In this manufacturing tolerance, some two tolerances will be there. One is the mold related tolerance. Okay. In the mold related tolerance, whichever changes will occur in the mold, for that we are providing one tolerance, that is the mold related tolerance. In this mold related tolerance, okay, and one tolerance is separate mold tolerance, which includes manufacturing and wear tolerance. Okay, in this mold related tolerance, two types will be there. One tolerance which covers the deviation due to the shrinkage, and one tolerance will cover the you can say that variation due to the manufacturing and wear. Combinedly it will be covered in the mold tolerance. Okay, so in this way these types of the tolerances will be there, or you have to consider before providing the total tolerance value. Okay, and process related tolerance, here all process parameters you have to consider. Whichever processed pressure, temperature, in cooling channel will be used, depending on that some tolerance you have to provide there for changes in the process parameters that will cover under this process related tolerances. Okay, so in this way the total tolerance will be provided in the plastic part by considering the operating tolerance and manufacturing tolerance. And to provide the manufacturing tolerance, you have to consider all mold related tolerances and process related tolerances. In process related tolerances, you have to consider the change or variation in the dimensions due to the process parameters. And in mold related tolerances, variation or deviations which will be there due to or factors related to the mold. It may be shrinkage, due to shrinkage, or it may be due to manufacturing of that mold, during the manufacturing of that mold, or due to the wear. Combinedly these four will give you the mold related tolerance. Okay, so these are the tolerances in the plastic part. And after this tolerances in the plastic part, we will move toward the allowances in the plastic part. If you are having any difficulty in the tolerances, you can ask me. Okay. If all points are clear, we will move towards the allowances. Okay. Now, what are the allowances? Allowances are the intentional variation or differences in the dimensions to take care of proper fit. Okay, these are intentional variations provided. Okay, we are intentionally providing it to achieve certain objectives. These will be termed as the allowances. These are termed as the allowances. Now, I think in the casting chapter you have studied this. Different types of the allowances are there, like shrinkage allowance, draft allowance, machining allowance may be there, distortion allowance may be there. But in case, as far as the allowances in the plastic parts are considered, two types of the allowances will be there: shrinkage allowance and the draft allowance. Now, what is the meaning of the shrinkage allowance? The shrinkage allowance is provided for compensating the shrinkage. Okay, whichever reduction in the size of that particular component will occur, that we have to provide. It will be termed as contraction allowance or shrinkage allowance. Okay, due to the solidification or cooling, some change in the dimensions will be there, reduction in the size will be there. For that, okay, for that shrinkage allowance or contraction allowance is provided, and the draft allowance. Okay, after ending of the solidification process, the particular component you have to remove it from the mold cavity, you have to take out. Okay, for proper removal of that manufactured component or end product from the mold cavity, one allowance is provided, that is termed as draft allowance or taper allowance. Okay, for proper removal of the manufactured part or end part from the mold cavity, one allowance is provided, it is termed as the draft allowance or the taper allowance. And uh, to compensate the shrinkage due to the solidification process, reduction in the size will be there, that will be termed as the shrinkage. And to compensate it, when allowance is provided, that is termed as shrinkage allowance or contraction allowance. Okay, and these are intentional variations or differences in the dimensions to take care of the proper fit. Okay, proper fit or proper removal, or to obtain the proper component with the desired shape and size. So these two types of the allowances will be provided. If you are having any difficulty, you can ask me. Okay, now we will discuss it in brief. Shrinkage allowance and the draft allowance. First, we will discuss the shrinkage allowance. Okay, this is the shrinkage allowance. Okay, shrinkage is nothing but a reduction in the dimensions of that component. Or here, this is nothing but suppose one processing method you are using, reduction in the dimension will be there during the cooling or during solidification process. This will be termed as shrinkage. Okay, and for this shrinkage, to compensate this shrinkage, one allowance is provided, that will be termed as shrinkage allowance. Okay, so this is the, suppose this is the required product size, this one internal product size, this is the required product size, but actual pattern used will be of this size, bigger size. And whichever difference is there, to compensate the shrinkage, this much difference we are providing. From the required size, we are using the additional size pattern. Okay, additional size pattern we are using. So this additional size here, whichever portion is highlighted with the inclined lines, that is nothing but our shrinkage allowance or contraction allowance. Shrinkage allowance or contraction allowance. Due to the solidification or cooling, you will get the end product of this internal shape. Okay, this is the required size, but you have to provide the pattern with the larger size by providing this much shrinkage or contraction allowance, because this much amount of shrinkage will occur during the cooling process or solidification process. Okay, so this highlighted portion by the inclined lines is the shrinkage allowance or contraction allowance. This is termed as shrinkage allowance or contraction allowance. Now, there are different types of the shrinkage allowances. Okay, related to, so this is just content beyond syllabus, you can consider it. The different types of the shrinkage allowances. Okay, liquid shrinkage, solid shrinkage, and shrinkage in solidification and cooling. Three types are there. This you can consider as a content beyond syllabus. Okay, they are not going to ask you any questions related to this. But for your information, I have collected this. This is the liquid shrinkage. Okay, okay. These diagrams I have collected for the metals. Don't get confused. For your information only, I have collected this. And diagrams will be here. Molten metal word will be there. Okay, just you have to understand the concept here. Okay, liquid shrinkage. So this is the initial diagram. You can say that this is the mold, and this is the molten raw material. This is poured in the mold. Okay. Now reduction in the level due to the liquid contraction. Okay, this liquid will get reduced. Okay, before solidification of that molten material, some contraction in the size of that liquid will occur. Okay, this is in liquid state only, and reduction is occurred here. Reduction is occurred here. Okay, this will be termed as liquid shrinkage. Liquid itself shrinked before solidification process. Liquid itself will shrink, or you can say that reduction in the size of the liquid itself before actual solidification occurs. This will be termed as liquid shrinkage. Then this is the solid shrinkage. Okay, this is the solid shrinkage, reduction in the height due to solidification. After solidifying or after solidification, some shrinkage will be there. After solidification, some shrinkage will be there. This will be solid shrinkage. Okay, here you can say that this is the reduction in the size. This will be termed as the solid shrinkage. Then next is the shrinkage in solidification and cooling. Okay, here shrinkage in solidification and cooling means at this corner also one shrinkage is there due to the solidification and cooling, and amount of liquid also get reduced. Okay, liquid contraction will be there, and at the corners, okay, at the corners also solidification will also occur. Okay, at corners solidification will, due to the solidification, shrinkage will occur, and some liquid will get reduced. Here combination will be there. Solidification at the corners or the walls which are in contact, liquid wall means the where wall and liquid is in contact with each other, there solidification will occur. Due to that, reduction in size will occur or shrinkage will occur, and some shrinkage will be there or a reduction in the size of that actual liquid also. Okay, this will be shrinkage in solidification and cooling. These three types of shrinkages will be there. Just you have to remember that some reduction in the size will occur, that will be termed as the shrinkage. Now, there are certain parameters. So this is in this you have to explain in this shrinkage allowance. Okay. During the solidification and cooling process, some reduction in the size will occur, that will be termed as shrinkage, and allowance is provided to compensate it, is termed as shrinkage allowance. Now, this shrinkage allowance in your plastic material, it depends on these factors. Okay, these factors will be holding pressure. Okay, these factors will be here: holding pressure, then holding pressure time, holding pressure and holding pressure time, then mold temperature and melt temperature. Okay, melt temperature and mold temperature, then wall thickness. Okay, wall thickness of the plastic part, and depending on the process, other parameters may be there. Suppose if you are using injection molding, then injection rate. Okay, depending on this, you have to provide the shrinkage allowance. And how these parameters will affect the shrinkage allowance, we will discuss one by one. Holding pressure. As holding pressure increases, as holding pressure increases, shrinkage allowance value goes on, or it decreases. Shrinkage allowance decreases. Okay, holding pressure is our first parameter. Then second parameter, holding pressure time. As holding pressure time increases, shrinkage allowance decreases up to a certain range, and after certain value, after achieving certain value of that shrinkage allowance, then holding pressure does not have any effect, means it will remain steady. Okay, if you increase the holding pressure time, it does not affect the allowance value. Okay, till some particular value, the holding pressure time will decrease the allowance. But after a specific attending a specific value of that shrinkage allowance, if you increase the holding pressure time, it does not affect the shrinkage value. Okay, so next parameter is the mold temperature. As we are using the increasing the mold temperature. Okay, as we are increasing the mold temperature, shrinkage allowance value will be, you have to provide more shrinkage allowance value. Okay, more shrinkage will be there, more shrinkage. Okay, this will be same for melt temperature also. As if suppose you have used more melt temperature or more mold temperature, automatically shrinkage will be more. That's why you have to provide more shrinkage allowance. Okay, in the process, if suppose more mold temperature or melt temperature is there, then shrinkage allowance will be more. Then wall thickness. As thickness of the part, wall thickness of the part, plastic part increases, then you have to provide the more shrinkage value. As part becomes more thick and thick, shrinkage allowance value will be more there. Okay, and in the suppose you are using the injection molding, then at injection rate, up to a certain extent, it will decrease the shrinkage allowance. And after that particular point, if you used more values for that, or higher values for the injection rate, then the shrinkage allowance will be more, you have required, or more shrinkage allowance will needed to be provided. Okay, so these are some parameters which will affect the shrinkage allowance. In that parameters, holding pressure time, mold temperature, melt temperature, and wall thickness, these are some common parameters. Okay, that will affect the shrinkage allowance. Okay, same here, I have explained or collected this same parameters in the these diagrams or these curves, simple curves. Okay, effect of holding pressure on the shrinkage allowance, effect of holding time on the shrinkage allowance, effect of the part thickness, okay, an effect of melt temperature, mold temperature, and injection rate. Then the next allowance type of the allowance is the draft allowance in the plastic part. Okay. Now here in the first few points, it is explained why this draft allowance or taper allowance is provided. When the manufactured part is removed from the mold, the parallel surface to the direction. Okay, I will explain it with the diagram. Suppose this is your manufactured part and this is the mold. When you are removing that part from the mold, okay, this is the direction of the removal. With the help of ejector pins, whenever you are ejecting it from the mold cavity, these surfaces, okay, there will be some friction here between the wall of the mold and wall of the manufactured part, and due to this friction what will happen, this final product or a plastic part may get damaged. To avoid this damage, this instead of using this vertical walls, we are using the taper walls in this mold. Taper walls are provided. So this is nothing but the draft or taper allowance. Okay, this is nothing but the draft. You can see here, this is the draft or taper allowance provided for removing the plastic part, manufactured plastic part, after ending the solidification process from the mold cavity without damaging it. Okay, for safe removal of the part, some taper or some draft is provided, that will be termed as draft allowance or taper allowance. Okay, you can see here in this diagram, this is the final product or solidified product. This is the mold cavity. From this we are going to remove it. During this removal, part may get damaged. To avoid this, some papers or allowances, draft is provided. This will be termed as draft allowance or taper allowance. Okay. And now generally in these plastic parts, zero point 0.5 degree to 3 degrees used. Generally in the plastic parts, here they have mentioned 1 to 2, but generally for some plastic parts, 0.5 degree draft is used. Sometimes you can go for up to 3 degrees. Okay, so this is the draft allowance, and this draft allowance depends on the we are using, then which mold material we are using, okay, which molding method, mold material, and shape and size of the mold. Okay, depending on this draft allowance in the plastic part will change. So in this way, in this session we have discussed this. Okay, in next session we will see some design guidelines. Okay, I will summarize the today's session. In today's session, what we have started with what is the meaning of the tolerances. Okay, what is the meaning of tolerance and factors affecting these tolerances in the plastic parts. Okay, then how to calculate the total tolerance by considering manufacturing tolerance and operating tolerance. And in that manufacturing tolerance, you have to consider mold related and process related tolerance. Okay, we have discussed this in brief. uh, which kind of the tolerances are there in the plastic parts. Then you have studied what is the meaning of allowance and which kind of the allowances are there in the plastic parts. Two types of the allowances are there in the plastic part: shrinkage allowance, okay, and then factors affecting the shrinkage allowance, like holding pressure, holding time, mold temperature, melt temperature, wall thickness. Okay, various parameters affecting the shrinkage allowance. What is the meaning of draft allowance or taper allowance, and factor affecting the magnitude of taper allowance or draft allowance. So we have learned this. in this today's session. If you are having any query, you can put that in the chat box. Otherwise, I will stop this session here only. Thank you for attending this session. You can put your roll number in the chat box for attendance purpose. Okay, from next session, we will start the design related consideration. Okay, already we have discussed the concept of minimum wall thickness. Okay, wall thickness is a most important aspect in the designing of the plastic part. Okay, that already we have discussed. From next session, we will discuss how the suppose while designing the ribs, why ribs are designed or provided, and how you have to decide their dimension, then coring, then corners. Okay, these are slides are there why coring is required, some design guidelines for coring, then ribs, again some design guidelines related to the drafts. Okay, so that we will discuss in the next session. Okay, in this today's session we have completed this uh, allowances, and that shrinkage allowance and factors affecting the shrinkage allowance. Then draft allowance we have discussed, and we have discussed the tolerances in the plastic parts. Okay, so I will stop here. Thank you for attending this session.